Hey, we're going to do some example problems for magnetism. So let's say that we have a duck flying horizontally due north at 15 meters per second and it passes over Atlanta. At Atlanta, the magnetic field of the Earth is 5 times 10 to the negative fifth Tesla and directed, that's supposed to say 60 degrees, but it took away my exponent there, but a direction of 60 degrees below the horizontal line running from north to south. The duck has a positive charge of 4 times 10 to the negative eighth coulombs. What's the magnetic force acting on the duck? This actually does happen to birds. They gain a charge by flying through the air, and then there's a small force on them due to their motion within the Earth's magnetic field. So let's lay out what we know. We know the velocity of the duck is 15 meters per second. We know that the magnetic field is equal to 5 times 10 to the negative fifth Tesla. We know that the charge is equal to 4 times 10 to the negative eighth coulombs. Ooh, this isn't as sensitive as I was hoping. And we know theta is equal to 60 degrees. So if we drew a picture of this, we have the velocity of the duck going due north. And then 60 degrees below the horizontal. So it would actually be like into the page, but we'll draw it like this. We have the magnetic field. Oh, but magnetic field points from north to south. And the magnetic, remember the Earth has a magnetic south at the north. So the magnetic field will point that way. And then this is 60 degrees. So we look at our equation sheet and we find the equation force equals Q times V, so charge times velocity times magnetic field times sine of theta. And that gives us the magnitude of the force, which is why you have the order or the absolute value bars on your equation sheet. I'm not going to write those, and then we just plug in numbers. So we have F equals our charge, which is 4 times 10 to the negative eighth coulombs, times our velocity, which is 15 meters per second, times the magnetic field, which is 5 times 10 to the negative fifth Tesla, times sine of the angle. And remember that the angle theta is the angle between the velocity and the magnetic field. So that's 60 degrees. So our force is 2.6 times 10 to the negative 11th newtons. Now we have to figure out the direction. To do the direction, you're going to use your right hand rule. So we know, if we use our right hand, that we're going to take our thumb and we're going to put it in the direction of the velocity. So put your thumb due north. Then you're going to take your fingers, which are your magnetic fields, and you're going to point your fingers in a direction that is at 60 degrees below the horizontal line that goes from north to south. So that should be like this. And so basically your 60-degree angle is right here between your thumb and your fingers. And which way does that palm push? It pushes to the west. I know that's hard to show you on Zoom, but the direction should be west. So go ahead and practice your right hand rule because you will need to use it on the test. Okay, let's try another one. A thin horizontal copper rod is 1 meter long and has a mass of 50 grams. What is the minimum current in the rod that can cause it to float in a horizontal magnetic field of 2 Tesla? So let's write out what we know. We know the length of the rod is 1 meter. We know that the mass is equal to 50 grams, which is 0.05 kilograms. We always want to be in SI units. We know the magnetic field is equal to 2 Tesla, and we want to know what the current is. So if you think about what we are trying to achieve, we want this rod to be levitating, right? To be floating. So it's going to have a force of gravity acting down and a magnetic force acting up. And we want these two to be equal to each other. So we want the net force to be equal to 0. So if the net force is equal to 0, then the magnitude of force of gravity is going to be equal to the magnitude of magnetic force. So we know that the force of gravity is mass times gravitational field strength. And I'm going to flip these. So magnetic force is going to be 0.05 kilograms times 9.8 newtons per kilogram. And that gives me a magnetic force of 0.49 newtons. So now I can use, I'm going to choose a different color here so they don't run together. I can use my force from a current carrying wire. So if I look at my equation sheet, I can see that force on a current carrying wire in a magnetic field is equal to the current times the length times the magnetic field times the sine of theta. And the magnetic field and the length and the force are all vectors. And so when I isolate my current, I get magnetic force divided by length times magnetic field. And then I can plug in my numbers, 0.49 newtons divided by 1 meter times 2 Tesla. And I am left with a current of 0.245 amps. It's supposed to be an A, which is the answer. Great. So let's do one more. This is a problem with a mass spectrometer. Mass spectrometers are used to separate particles by mass. So if you have a whole bunch of small particles and you want to pull out maybe all of the gold atoms, then you could shoot them through a mass spectrometer and you could get the gold to separate from other things. So here's how it works. There is a parallel plate, basically two parallel plates. One is positive, one is negative. We can tell by the direction of the electric field that this one is positive and this one is negative because the electric field points from positive to negative. And there's these plates that are within a magnetic field. So the first piece is separating out the particles by their speed. So we know that the magnetic field is going to put a force on the particles. So this magnetic field is going to be putting a force on the particles by QVB sine theta, but theta is going to be 90 degrees. So I'm just going to leave that part off. So force from the magnetic field is QVB. Then we also know that the force from the electric field, this is a constant electric field. So the force from the electric field is going to be Q times the electric field because it's a constant electric field. So when it goes through this part, only the charges that have a specific velocity will go through this undeflected. If they're traveling too fast, then the magnetic field will pull on them more than the electric field. And if they're traveling too slow, the electric field will pull on them more than the magnetic field, and they will fall, and they won't, or not fall, but they will be deflected, and they won't make it through this part. So this part is called the velocity selector. We can see here that if they were positive charges, then the magnetic field, if we use our right-hand rule, we put our thumb in the direction of the velocity. We put our fingers in the direction of the magnetic field, which is going into the page. And then we can see that a positive charge would be forced upward by the magnetic field. we can also see that a positive charge would be forced downward by the electric field because we know that positive charges follow the electric field arrows. If it was a negative charge, then it would be pushed upward from the electric field towards the positive plate. And then the magnetic field, you can use your left hand to figure out which way it would be pushed. So you have your thumb in the direction of the velocity, you have your fingers in the direction of the magnetic field, and then your palm pushes down. So the magnetic field would push it downward. So those are opposite forces. The electric field and the magnetic field are pushing the charge, those particles, in opposite directions, those charged particles. And when they equal each other out perfectly, the charge can pass all the way through here. Then it gets to just the magnetic field. So out here, there's only a magnetic field. And the electric field is not acting anymore. So we know that when particles are moving in a magnetic field, they'll move in a circular motion because the force is perpendicular to the velocity. And so we can see that since it's moving in circular motion, out here, the net force will be a centripetal force. So it will be equal to mv squared over r. So the radius of the radius of the particle is going to be dependent on the mass because all of them are traveling at the same speed. That was established in this part right here. And so the particles will be divided according to their mass. And so we can divide atoms of different isotopes with different numbers of neutrons using this method. It's really cool. Okay, so let's do the problem. We start off with the things that we know. So our electric field is equal to 950 volts per meter. We know that our magnetic field is equal to 0.93 Tesla. We know that the mass of the particle is 2.18 times 10 to the negative 26 kilograms. And my negative sign is not very apparent. And then we know that the charge is, it says singly charged ion, which means that it just has one extra electron or it's missing an electron. But we don't know if it's positive or negative. To figure out if it's positive or negative, we look at this part over here. We know that in a magnetic field that's going into the page, the charge is being forced upward. So if you take your right hand and you have your thumb in the direction of the velocity and your fingers into the page, you're going to be pushing upward. So the right hand tells you what the positive charge does, so we know that it's a positive charge because it follows the right hand rule. So we do positive 1.6 times 10 to the negative, goodness, this is not very sensitive, times 10 to the negative 19th coulombs. And we know this number, this is a constant that's on your equation sheet. It's the charge of an electron. And we want to figure out what the radius is. So I'm going to start off by thinking about things that are happening. I'm going to change my pen color again. So we're going to think about things that are happening in the deflection chamber. So I'm going to work backwards. So this is the deflection chamber right here. In the deflection chamber, we know that the net force is equal to the magnetic force. So the net force is mv squared over r, since it's moving in a circle, and the magnetic force is qvb sine theta, but I already established that theta is 90 degrees, so our sine theta is just 1. So now I can see that I have one of my velocities cancels out. That velocity cancels with that velocity. And then I'm solving here for radius. So if I multiply by r over here and then divide by qb, I get r is equal to m. Wow, I'm sorry, I'm just not happy with how this is looking. Okay, I really have to push on this thing to make it feel me. So we have R is equal to M times V over Q times B. So in order to solve for R, we have mass, we have charge, and we have magnetic fields. We don't have velocity. So we're going to think about the velocity selector. And in the velocity selector, we know that we have the force, the electric force pushing down, and the magnetic force pushing up. Goodness. So we know the net force is equal to 0. So we know the magnetic force is equal to the electric force. So our magnetic force is Q, V, B sine theta, but remember theta is 90 degrees. And then our electric force is Q times the electric field. Now notice that our Q's cancel. And I can solve for V. V is just equal to the electric field divided by the magnetic field. So I can plug in numbers there and I get 950 volts per meter over 0.93 Tesla. So that gives me a velocity equal to 1,022 meters per second. So now I can plug this in to here. Go back to my teal. And I can just plug in numbers now for radius. So radius is equal to our mass, which is 2 times 10 to the negative, oh sorry, I forgot my 1/8. 2.18 times 10 to the negative 26 kilograms times my velocity, which is 1,022 meters per second. Whew, I'm crunching for space here. Divided by charge, which is 1.6 times 10 to the negative 19th coulombs. Times my magnetic field, which is 0.93 Tesla. So the answer that I get is 1.5 times 10 to the negative 4th meters. That is my answer. There we go. So just a recap on this. In this part, the particles are separated by speed because the force is dependent, the magnetic force is dependent on the speed. The charge cancels out because you want your forces to be equal here, so charges cancel. And charge doesn't affect your force in this part, but the speed does, and then the magnetic field and electric field are constant. Then it gets to this part, and this is where the charges are separated by speed. By mass. We know they're all going the same speed, so the radius at which they move is going to be dependent on their mass. So we can separate particles by mass using this method.